Hello friends, I Gaurav Murghare. Today I am going to discuss the topic of sampling theorem. This topic is very useful for the subjects like signal and system, digital communication and digital signal processing. So before proceeding on the sampling theorem, first we will discuss why we need a sampling. As we all know in the real world, whatever the signal are the analog signals. That means this signal can be our voice signal or any other signals. To process these signals, we use computers or the digital devices. So, first we need to convert these analog signals into the digital form because the machines only understand the digital signals. As we know that the analog signal is both continuous in time as well as amplitude, whereas the digital signal is discrete in amplitude and time both as well. To convert any signal from continuous time to discrete, we use the sampling process. And the samples or the measurement at the certain interval of time, we call those as the samples. So in sampling theorem, its statement says that for any continuous time signal which can be limited or represented by its sample can be recovered back only when the sampling frequency fs is greater than or equal to twice of the highest frequency component present in this signal. Or it can be also defined as if a signal is band limited to fm, that means if a signal is having only one frequency or many frequency components, but the maximum frequency component is denoted by the fm, then the sampling frequency should be greater than twice of fm. Otherwise, if the sampling frequency is lesser than twice of fm, that means 2 times of the maximum frequency component present in the signal, then it is very difficult to recover that signal. So moving on to the proof, first we will consider a signal xt which is having the band limited or the maximum frequency component as fm. The spectrum of the xt is also shown. I'm going to show it in my next slide, in next figure slide. So this input signal xt is multiplied with the train of impulses. This train of impulses is having a time period which is given as ts. This is also the sampling time, we can say. The output of the multiplier of this discrete signal is the sample signal and it is denoted by the yt. So I'm going to show you the figure. In figure, as you see, a signal xt, this is an sinusoidal signal, will consider that it is having the frequency or the maximum frequency of omega m. We can also know that if we are saying fm is the maximum frequency component present in the signal, so its unit is hertz. And if I am saying that the maximum frequency is having the value of omega m, then its unit is radian per second. We know that omega is equal to twice of 2 pi of f. So there should be no confusion in that. In somehow in the statement it is mentioned as fm, but we are discussing or describing in the figure by the omega m. So what we are doing? We are doing by multiplying this signal with this train of impulses. This is our basic signal and this is the train of impulses. This train of impulses del t is having the amplitude of 1, constant amplitude of 1 with the sampling time interval of 1 second or ts, we can say. So if we'll multiply, and we know that this ts is obviously the greater than this time period of this signal, so as a resultant, that means multiplication of these two signal, that means signal 1 and signal 2, we will get the resultant signal this as the 3. So in the figure you are also seeing these two figures at the bottom. What are these two figures? We know that xt is our signal, so if we'll convert this xt by using the Fourier transform tool, we will get a energy band spectrum or a spectrum like this. So x omega is the spectrum for any xt signal. Now we know that the train of impulses del t is having the same Fourier transform. That means if we'll convert this del t signal into the spectrum or the frequency domain, the resultant will be the same. The resultant will be the same. Please remember this term. So now what we are going to do, we are multiplying this s omega with the del of omega. Del of omega is similar to the del t. So the result will be is this signal. That means if we'll multiply it with x of omega, now consider this signal as the del of omega, because I already told you that the signal, that means the train of impulses, is having the Fourier transform same in the frequency as well. So now x of omega is multiplied with the del of omega, that means this single spectrum is multiplied with the train of impulses, then the resultant we will get as this in the format. So the spectrum is distributed, or the energy is distributed over the frequencies of omega s. The interval is the same, interval is the omega s. So to prove that, what we are doing, we are taking the signal xt which we are multiplying with the del t. Del t is the train of impulses. So what we are, train of impulses, we can show it by the trigonometric Fourier series. This is the formula for our trigonometric Fourier series. You are already know this. So coefficient a naught, an and bn is calculated by the trigonometric Fourier series. The value of a naught is 1 upon ts, 2 by t and 0 for the an and bn respectively. Now substituting these values in the equation 2. I am again moving to my previous slide. So what is the equation number 2? Equation number 2 is this, the trigonometric Fourier series. Substituting these values of a naught, an and bn in this equation, we will get the resultant like this is our value. So what this yt is representing? Yt is just representing that there is the factors of xt multiplied with the cos of omega t, xt is multiplied with twice of thrice and so on. So what this is showing? This is just showing, if we'll see the property of the Fourier transform, that any signal is multiplied with the cos of omega t, then its impulse is shifted in the left hand side and the right hand side. So this term twice of omega st into xt, the resultant will be these two terms. This energy is shifted at minus omega s and plus of omega s. Similarly for twice of omega s, these are the two terms for that. Now further, if we'll see, if the sampling frequency is greater than twice of fm, that is, we will easily recover. Now what we will do, if we have to transmit this signal, we can take the energy by applying a low pass filter over that, or any band pass filter, to get the energy for this thing. Now for the perfect sampling case, you know this, the end of this signal, that means omega m and omega m minus omega s minus of omega m will be the same point, this term. And what will be, if the sampling frequency is lesser than twice of fm, then it is a case of under